In this video, we're going to look at a variational form of the Helmholtz eigenvalue problem. Why are we going to do this? Well, first of all, it's fun mathematics, but more importantly, a second reason is that we will be able to use this variational expression to gain some sort of physical insights for what's happening with light distribution in certain structures. But that's for the second video. In this video, we're going to focus on the mathematics. What we're going to do is we're going to look at a certain variational form, and let's say the variational form has the following form. It's h with theta h divided by the scalar product of h with itself. And what we're going to deal with in this video is showing that this variational form is actually equivalent to the eigenvalue problem of the Helmholtz equation. This basically means that if we have a solution to this variational form, namely if we end up in a situation where we find a field distribution where delta j is equal to 0 for all possible variations around that field distribution h, then we would like to know whether this indeed results in us recovering our beloved eigenvalue problem for the Helmholtz equation, which is this guy over here. So that's the goal of this video. So obviously, for that reason, we would need to calculate delta j. So one thing we could do is start directly from this equation and replace here h by delta h. But this will turn out to be rather cumbersome because we will end up with a delta h in the denominator. And then we need to develop this in a series expansion. This will be very painful. So therefore, let me show you a little trick to simplify our lives a little bit here. We're going to just multiply everything by h so that we get rid of the denominator. So we end up with the following expression over here. H theta h. And let's call this expression number 1. And the strategy we're going to use is we're going to start from this expression number 1 and perturb it. So we're going to perturb it by replacing h by h plus delta h, but also at the same time replacing j with the corresponding j plus delta j. So this delta h and this delta j, they're not independent from each other. This delta j here is the delta j that you would get when you make this perturbation here, replacing h by h plus delta h. So our strategy will be to start from this equation over here and then make that perturbation. And then we get a perturbed equation, and then we subtract the perturbed equation from this original equation and see if we can use this to calculate delta j. So I suggest you pause the video now and try to do exactly that. Right, so let's focus on this first term over here, so JHH, and let's replace j by j plus delta j and h by h plus delta h. So let's already do some distributivity for j plus delta j in the first factor here. So this will give us j and then h plus delta h plus delta h, and then we have the delta j contribution, h plus delta h plus delta h. Okay, so this is what we get in the first term when we replace j by j plus delta j, h by h plus delta j, and then expand this first factor with j plus delta j. Right, for the second contribution, we need to look at the right-hand side. For the right-hand side, if we replace in h plus h, theta h, if we replace h by h plus delta h, we simply get the following. We get h plus delta h, theta h plus theta operating on delta h. And this is our perturbed version of equation number 1, and let's call this perturbed version equation number 2. Next step, as announced, we're going to subtract these two equations and then see what's going on. Obviously, we want to look at the linear version of this, so all the higher order terms, so with delta squared and stuff like that, we're just going to neglect this. We're interested in small values of delta j. So all of the higher order terms, we're just going to neglect those. Okay, so let's see what's going on. And let's first take a look at this first term over here, and then do distributivity of this scalar product here. So 2 by 2, this will give us 4 terms, and the first term will be JHH, and then we subtract equation 1 from this. And this is exactly the term that we're going to subtract, so this first term will just vanish. Let's take a look at the second term. That's a term that will not vanish, so we have J delta H, H, and then we have J H delta H. And then our final contribution will be delta H scalar product with delta H, but this is a second order term. This fourth term, we're just going to drop it. Okay. Next step is we need to look at what's happening over here. So we have a delta J over here, and then the first contribution will be delta J and then H, H. If you look at all of the other contributions, then we will notice that there will be at least 2 deltas over here, because there's also delta here in front with the delta J. So all of the other contributions, we'll just neglect them, and we're only left with this first contribution here, delta J, H, H. Okay. And then for our final contribution, we take a look at the right-hand side. So again, 2 by 2 giving us 4 terms. First one is if we combine this with this, but that's exactly what we will subtract then in equation 1. So the h, theta h, that just cancels. And then for term 2, we have h theta delta h. And then the third term will be a delta h with a theta h. And then the fourth term again will combine 2 deltas. So that's a higher order term. Let's get rid of it. Okay. So now we ended up with this equation over here. And actually you see that we will be able to use this equation to explicitly calculate delta j. Now the calculation for this is not difficult, but it's rather elaborate. So this is why I've lifted this out in a separate exercise video. But in this exercise video, you will show that you can calculate this delta j as being the following expression, theta h, and then we have a certain new quantity, which we will call g. And then we just exchange the order here. We have g delta h. And then we divide this thing by 2. And in this exercise, you will show that this mysterious quantity here is actually equal to the following thing, 2 divided by hh, and then a small monster here between square brackets, which is theta h minus h theta h divided by hh h. And some of the things that appear in this formula should start to look familiar at this stage. Okay, so now we have our delta j. Pause the video here and see if you can use this to finally make the step to the Euler's Lagrange equation of this particular variation expression, and see if you can indeed show this is equivalent to the Helmholtz equation in its eigenvalue formulation. So to recall a little bit what our goal was and where we started from this particular variation expression. And then we were trying to figure out what was the delta j, the first variation of this variation expression, and what would happen when we put this equal to 0. So now we're at a stage where we know what delta j is. Delta j is equal to the following expression. Now we can ask ourselves the question, what happens if delta j is equal to 0? But not just for a lucky choice of our field distribution, no, but rather for any perturbations of that field distribution that you can think of here. Now, if delta J should be equal to 0 for all possible variations around our solution H, then if looking at this expression, you see that the only way to satisfy that is by making sure that the new quantity that we introduced here, this G, that one should be equal to 0. Looking at this expression, then it's easy to figure out under which circumstances that happens, namely if theta H is equal to theta H divided by H. So what's happening here? Well, we have a certain equation where we have a theta operator operating upon a magnetic field, and we get back that same magnetic field but multiplied by a scalar value here, which will be the eigenvalue. This is indeed a scalar. This is a scalar product divided by a scalar product. So this is a scalar as it gets. And this is indeed the eigenvalue of this particular problem here. So what we get from this is that we only get a solution if our H satisfies this particular eigenvalue problem. And that's the eigenvalue problem of the Helmholtz equation. So we were looking to show indeed that this was the equation that would pop up. And what's more, something else that we can gain from our calculation here is that the eigenvalue actually is equal to J. So the value that our variational form takes when we have a solution will be equal to the eigenvalue of that field distribution in our Maxwell-Helmholtz eigenvalue problem. So this is indeed what we set out to prove.